Somewhere in the depths of space, in the impenetrable darkness surrounding black holes, may lie the answer to one of the universe's greatest mysteries. For centuries, scientists have puzzled over the question, what is dark matter? And now, it seems, we stand on the brink of a staggering discovery. Have scientists found dark matter near black holes? Join us, and together we will unravel this mystery. You're watching Space Made Simple, and I'm Cosmo. Today, we'll discuss the possible connection between black holes and another dark part of the universe, dark matter. An article published in the Astrophysical Journal Letters describes the potential discovery of indirect evidence of dark matter near black holes. As we know, according to current theories, to explain the structure of the universe as we observe it, there must be dark matter in the universe. Moreover, there needs to be 5 times more dark matter than the ordinary matter that makes up you and me, and everything else we see. The mass of ordinary matter isn't enough to explain the dynamics of galaxies and galaxy clusters. Well, there are other effects, but we have yet to directly find dark matter and understand what it is. However, another step might have been taken towards understanding it. Black holes have long been associated with dark matter in one way or another. Black holes themselves have been suggested as a form of dark matter or the missing mass. However, this theory is currently unpopular. But that's not what I'm talking about. It has long been assumed that the density of dark matter near black holes could be higher. Dark matter is believed not to interact with light or electromagnetic radiation, but it does interact gravitationally, and black holes have gravity. In general, if black holes really accumulate more dark matter than average across the galaxy, it could potentially be detected. For instance, if dark matter consists of particles unknown to us, one theory suggests these particles could annihilate, releasing gamma radiation in the process, and we are capable of detecting gamma radiation. Therefore, if our assumptions are correct, and there is a higher concentration of dark matter near black holes, and we detect an additional signal in the gamma range that we can't explain by anything else, perhaps we've found a signal from annihilating dark matter. Scientists have attempted to find such a signal, focusing mainly on supermassive black holes at the centers of galaxies. But so far, no such signal has been detected. However, this doesn't mean there isn't a higher concentration of dark matter near black holes. There might be other ways to detect signs of its presence, and the new article is precisely about this. The idea is to use, firstly, not supermassive black holes, but stellar ones, and secondly, to use binary systems consisting of a black hole and a star. If the star is close enough to the black hole, and there is indeed more dark matter there, it's possible that the dark matter and the star could interact through gravity, which could influence the star's behavior, and we might attempt to detect this. It should be noted that some anomalous behavior of such stars has already been observed in the past, which was attempted to be explained by other mechanisms, but not very successfully. What anomalous behavior? The orbit of a star in a binary system gradually decreases. It very slowly but surely approaches the black hole. This orbital decay is observed, for example, in satellites in near-Earth orbit, including the ISS, though they are seemingly in space, but at an altitude of several hundred kilometers, there is still an atmosphere, albeit a very thin one. To maintain a certain altitude in orbit and counteract Earth's gravity, a satellite needs to maintain speed. But even the very weak atmosphere gradually slows satellites down, leading to a decrease in their orbit and eventually to falling to Earth. And a similar decrease in orbit is observed in stars in a binary system with a black hole. We see this by measuring the star's orbital period over a long time. If we see it gradually shortening, it means the star completes its orbit faster and gets closer to the black hole. But most interestingly, in some systems, this reduction in orbital period happens noticeably faster than models predict. This has been attempted to be explained, for example, by braking against a disk of matter that might be present in the binary system, or by the action of magnetic fields. But all these explanations fail to match real observations satisfactorily. Here's where dark matter enters the stage. The authors of the study used two relatively nearby black holes with companion stars. The observed reduction in their orbital period differs very significantly from the predicted values. The theory predicts it should shorten by about 2 to 100 milliseconds per year. But observations show that in these systems, it actually decreases by 1 millisecond per year. So, there's a 50-fold discrepancy between theory and observation. The authors of the article used computer simulations, applying the so-called model of dynamical friction with dark matter. In their simulations, the decrease in the orbits of stars matched the real observations quite accurately, unlike models that did not include dark matter near black holes. But what exactly is the model of dynamical friction? The idea has been known for several decades and was originally proposed by none other than Chandrasekhar. I mentioned how satellites in Earth's orbit gradually decrease due to the atmosphere's influence. Its particles can literally collide with the device, causing it to lose energy and, consequently, slow down. Here we have direct contact and conventional friction. With dynamical friction, two bodies don't need to come into direct contact, but can interact with each other through gravity. In a previous video, I mentioned gravitational maneuvers using a mothership. We use the gravity of a more massive body to accelerate, or conversely, slow down a passing spacecraft. Gravitational interaction allows two bodies to exchange angular momentum. One body loses it, the other gains it. This is the simplest variant, where we have two bodies, but situations can vary. One body can pass through a cluster of many others, for example, less massive ones, and being close enough, they can also exchange energy in the process. A more massive body, through its gravity, kind of pushes away, or in other words, accelerates other bodies around it. But energy can't come from nowhere. Therefore, in doing so, the more massive body loses its energy. During such movement through a cluster of less massive bodies, a kind of tail of smaller bodies can form behind the larger body, and they will slow it down with their gravity. This logic can be applied to dark matter, as it interacts gravitationally with ordinary matter, which is precisely what the authors did, obtaining results that match observations. Does this mean there's indeed a higher concentration of dark matter near black holes? Not necessarily, but that's why the article's title mentions indirect evidence. The research is also interesting because it tackles two problems at once, providing indirect confirmation that a clustering of dark matter could be present near black holes, while also addressing the issue of anomalous breaking of stars near black holes. We are just beginning to unravel the mysteries of dark matter and its connection to black holes. This journey beyond our understanding of the universe is still full of undiscovered mysteries. Don't miss the chance to be part of this amazing scientific adventure. Subscribe to the channel to learn more and stay with us on the edge of scientific discoveries. Thank you for watching.